What is up, everybody? It is 8:54 on a Thursday night, which means you know what time it is. It's time to do some statistics on the Mathnasium. Let's jump right in. This is 2-2 day one density curves and the normal distribution. It's a big day for us. I'm really excited, and it's been a long day for me. So let's go ahead and jump in. Right away, let's take a look at this class data that we did. We played three little activities last time you were in class. We had everybody roll some six-sided dice, and we see that we kind of, like we would expect if we were to continue to do this, the levels of these die rolls, are going to stay roughly the same. We could, do thousands of rolls, and they're going to still kind of hover around the same number or the same value. They're going to stay roughly the same height. It turns out, I kind of mentioned this before, this is called, if they were to stay roughly the same height, we would expect them to do. I mean, we're going to see natural variation with the rolls, but this is called a uniform distribution, which we're going to talk about here in just a minute. Okay. The uniform distribution. The other distribution we saw was when we were flipping trying to toss the pennies as close as we could to the target. And a lot of people got really close from 5 feet away, but there were a couple rollers that got away from people, maybe rolled really, really, really far. So you could say this is heavily skewed to the right. So if you have that little sheet of paper out and you want to draw the actual shape, this is heavily skewed to the right, which means that the mean will be pulled in the direction of this outlier out in this space here. And then we saw another one trying to stop our stopwatch on exactly 5 seconds, and we recorded the times. This has a different shape. It looks roughly symmetric, right? Roughly symmetric. This top one also roughly symmetric. If we were to really kind of continue this pattern, it would end up being that. And so for the top and the bottom, the uniform distribution, and this one down here, the mean and the median are probably pretty close together. Down here, I would imagine the mean's going to be pulled to the right. So these are all different distribution types. I don't know what the exact distribution of this one is, but this is uniform, and this one down here turns out to be something called a normal distribution. So we're going to explore those here in just a minute. But I'd like you to know, that kind of blanket metaphor. If you were to kind of lay a blanket over top of this and drape it over the top of the curve, we would get this kind of flat blanket shape. If we were to lay a blanket over our observations on this one, it would be kind of bumpy, and we'd have a little thing going on over here where it's skewed way, way out. And if we were to lay a blanket over top of this one, it would kind of look like so. And I think I'm kind of melting my computer here, but I'm going to take a stab at this. So all of these shapes and these blankets that I'm drawing kind of have a name, okay? The curve of the blanket. Now, I got to be careful here because the blanket for these things wouldn't be on top, but we'll get there in just a minute. But this general shape that can kind of approximate where these observations are going to lie has a name, and it's called a density curve. A density curve is always above the horizontal axis for what we're graphing. And then the density is the proportion of observations that fall in a certain region. So the area under the curve from A to B, now there is no A or B drawn here presently, but the area under the curve from A up to B estimates the proportion of all observations that fall in that interval. So the area here, if we could find the area of this shape, we'd be able to find the proportion of observations that fall in that interval, which would really give us the probability of an observation being measured between these two values. So here we have the minimum for distribution, or for the density curve. And here we have the maximum for the density curve. Now the total area underneath this whole curve from here to here has to be 1 for a density curve. That would be 100, that meaning like 100% of the observations for the distribution fall between the minimum of the maximum. And 100% in decimal form would be 1. So the area under this has to add up to 1, but we can look between observations and we can start to say, oh, I want to see how many would fall in this region. And that's going to give us the proportion of those observations, so we can make predictions about how likely something is to happen, and we will do that today. And these are actually functions. You know, some of these density curves have functions that we can find and we can talk about, which is pretty cool. Now, many of you have not taken calculus, but those that have might recognize this. In calculus, the area under the curve is called an integral, and statistics and calculus are married very well. You're not have to do calculus for this class. Our calculators are going to do it for us. So I'm kind of tricking you into doing calculus. You'll be doing calculus, but you don't know you are. So yeah, we can look at, say, the area under some of these blankets, and we can take a guess at the likelihood of receiving an observation in that region. It's really exciting. Okay, so recap. Area under here has to be, under the total thing has to be 1, but that green area is just the likelihood of something falling between those two events. So let's take a look at specific distributions here, and then we're going to see an example and do some calculations. Okay, let's take a look at a uniform distribution. Now, we don't need calculus to find the area under this because it just forms a rectangle. Uniform distribution, which is the rolling of dice or generating a random number between 0 and 1. These are all things that it could be. So anytime, they kind of are broken into two categories. You have the category when you're trying to find, for a uniform distribution, they run from 0 up to some number k. And so the height of this density curve, or the height of this line, since the area underneath the curve has to be 1, we can calculate what the height of the line is. So to do that, we would just say, we know that this is a rectangle, we know that this length is k, and we'll call this h, our height. I know that k times h, the length times the width of a rectangle, has to be equal to 1. So that means the height of the rectangle, or the density value here, is going to be, if we divide both sides by k, 1 over k. And this will make more sense when we see an actual example. Okay, but sometimes, because remember, underneath this rectangle, the rectangle has area equal to exactly 1. But sometimes you got to be careful because they don't start at 0. They might start at some value a and go up to some value b. Now the area under this curve still has to be exactly 1. So let's see if you can figure out what the height of this curve is if you're running from a to b. So you can pause the video, you can try it, but just use that formula. So here is our height. So the area of this rectangle has to be equal to 1. So we can say the height here is just h. And what is this length? Well, that length is going to be b minus a. So to solve for the height of the density curve, we can just say that the height in this case, if you don't start at 0, right? If you don't start at 0, then the height is 1 over b minus a. And since with uniform distributions, since they're symmetric, that would mean that the mean is approximately equal to the median once you calculate your distribution there. Okay, perfect, great. This is uniform distribution. Let's see an example. The internet reaction time test asks subjects to click their mouse button as soon as a light flashes on the screen. This sounds similar to the stopwatch. The light is programmed to go on at a randomly selected time after the subject clicks start. The density curve models the amount of time the subject has to wait before the light will flash. What height must the density curve have? Justify your answer. I think we're still on red. So here's our density curve here. I know that under this curve, you have to have the area 1, and that forms a rectangle. So to find the height of the curve, all we have to do is say, okay, well, I know that the height of the curve is equal to, let's do it from the start here. I know that the length of my rectangle is going to be 5 minus 1, and I know that the height of my rectangle, we're going to call this h, and that's what we're after. So 5 minus 1 times h is equal to 1. 5 minus 1 is, of course, 4. So the height of my rectangle would be 1 divided by 4, or 1/4. So the height of the density curve here, or density line, as we would say, which is the time in seconds. So basically, the computer is going to randomly select a time between 1 and 5 seconds for you to wait after you click start, and then wait for you to click and see how fast your reaction time is, basically. Okay? So the height of the curve there is 1/4, or it's a decimal, 0.25. Perfect. That's the density is 0.25. Okay, let's keep moving. All right, let's take a look at this one. Internet reaction time tests. Again, the same screen. About what percent of the time will the light flash more than 3.75 seconds? More than 3.75 seconds. So let's take a look here. More than 3.75 seconds. So where does that fall on our graph? So we can look to figure this out. We can answer, we can take the area under the curve. So here's 3.5, here's 3.75. So we're looking at from here to here. What percentage of the time will the light flash more than 3.75 seconds? So this is really easy to calculate. We already know that the height of this is now 0.25, or 1/4. And I know that the length of that is 1 plus, that's 3.75, so this is 1 plus 0.25, or 1.25. So what percent of the time will the light flash more than 3.75 seconds? All we have to do is say, well, that's going to be the area equals 1.25 times 0.25, which will give us, 1.25 times 0.25, which will give us 0.3125, which is 31.25%. So roughly 31% of the time, the light is going to take longer than 3.75 seconds after the subject clicks start. Last question regarding this problem. Calculate and interpret the 38th percentile of this distribution. So this is different. So what this is saying is it's saying, all right, we know this, this is a rectangle. Whoops, let me change my color. We know this is a rectangle, so we have that same formula, area equals the, length times width, or base times height, whatever you want to call it. We'll use base times height for this rectangle. The question here is, it's asking us calculate and interpret the 30th percentile. So what time will have 38% of the data over here to the left? Okay, so how do we calculate that? Well, that means we need 0.38 has to be equal to, I don't know what the base is exactly, but I do know what the height is. So if we're looking at this and we want to figure out what we're doing, we basically just have to say, well, what value, this is going to be What's the base going to be? It's going to be some value in here times the height, which is 0.25. So my base is going to be, in this case, I don't know where it falls. This length is going to be some number x minus 1, because we're starting at 1, times the height of my curve. So we have some basically rectangle in here, and we don't know what it is. I'm just going to guess that it looks something like that. I don't know what this value is, x. I know that the length of this is going to be x minus 1. So we would say times 0.25. And now we have an equation to solve. I know that the area in here is going to be 0.38. So we would divide both sides by 0.25 to get 0.38 divided by 0.25, which is 1.52, equals x minus 1. And then add 1 to both sides to get x equals 2.52 seconds. So my drawing wasn't super accurate here, but it also says interpret. And my computer's probably going to crash when I try to interpret this. But the interpretation this is about, it is going to crash, oh my gosh, about 38% of the time about 38% of the time, the light will flash before 2.52 seconds. Come on, computer. Yeah, cool. Sweet. That's how we use the uniform distribution. All right, let's keep moving. So the second distribution, the rolling of the penny, was a skewed distribution. So one thing, I'm not going to say a whole bunch here, but I just want to remind you that if you're looking at the density curve of a skewed distribution, when this happens, the median is typically to the left of the peak. If it's skewed to the left, median is to the left, and the mean is even further to the left. If it's skewed to the right, the mode is kind of the peak, the median is to the right of the mode, and the mean is even further to the right of the median, because that mean is being affected by the outliers there. Okay, cool. Little refresher. Okay, the next one we're going to talk about is this normal distribution. And this slide is also probably going to kind of crash my computer. So normal distribution has this nice symmetric single-peaked bell-shaped curve that we look at. Okay? And when we're dealing with a normal distribution, the center of the normal distribution is, let me fit this here, the center is what's called the population mean, which I mentioned once, which is mu. This is the Greek letter mu. Some people it looks like an M. It's like a U with a tail on the front. So the Greek letter mu. But since this is symmetric, it's also approximately centered on the median, which is kind of exciting. So you can see right down here, if I come down, boom, 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 this is going to be our population mean, mu, right there. So this is our average. Now, you can actually also view the population standard deviation for the density curve of a normal distribution. Now, the normal distribution that we saw was us trying to stop our stopwatches. Okay, so here, the way that you find the standard deviation, there's a couple different ways to find it. The first is you go to kind of where it touches this distance here, and then you take that distance and you divide by 3 to find where the standard deviation is. The other way you can do it is, you see how the top of the curve is kind of, it looks like it's got a hat, right? It's concave down. The hat is opening down like this, but right here, it looks more like a cup, like it's slanted up like this and it's concave pointed up like this. So the standard deviation is the spot, it turns out, where it changes between the hat or the cap looking, so concave down and concave up. And it's kind of hard to see, but where does it get straight, basically? Where does the line stop being bent and where does it become straight? And that, I would say, is somewhere in this region. So we can kind of draw a dashed line down. The population standard deviation that we use looks like an R with a loop, so you guys can practice writing that like this. It's called sigma. This is lowercase sigma is the population standard deviation. So this value here is equal to mu plus one single standard deviation. Now if I take the width of this and I go up one more time, like so, this would be mu plus 2 standard deviations. And when I go all the way up even further, I've maybe made this a little too wide, but that's okay. This is mu plus 3 standard deviations over here. And the same pattern occurs if I go to the left. Okay, so down here, this is mu minus 1 standard deviation. Down one more is mu minus 2 standard deviations. And down one more is mu minus 3 standard deviations. Now the reason we're doing this is it turns out there's a really important rule about normal distributions. Normal distributions have this amazing characteristic where roughly 68% of the distribution is held within 1 standard deviation of the mean. So between here and here, we have 68% of the data. Now, since they are symmetric, and this is the halfway point, we know that there is roughly 34% of the data to the left of the mean, 1 standard deviation, and 34% of the data to the right of the mean, 1 standard deviation. Okay, great. There's also, within 1 standard deviation of the mean for a normal distribution, this is only for a normal distribution, there is 68% of our data. And so we can go back to that original model. You know, we could sit here and calculate what the mean and standard deviation were. We could see how many things fell in there, and it's going to be really within 1 standard deviation. And it's going to be really close, because these were normally distributed to 68%, which is kind of cool. All right, we also know, it turns out, that within 2 standard deviations of a normal distribution, we would expect to see roughly 95% of the data. So 95% of the data is going to fall within 2 standard deviations. Now, if we do some simple math here, we know that if this is 95 and this is 68, then 95 minus 68 is what's going to be in these 2 sections. So I can go to my calculator, and I can say 95 minus 68 is 27, divided by 2 is 13.5. So if I zoom back in, I'm going to go down so we can see this a little bit better. That's going to be 13.5% of the data is in this section here, and 13.5% of the data is in that section there. So between the first standard deviation and the second standard deviation, we expect 13.5%, and similarly down here. And then the last rule is within 3 standard deviations. I'm wondering how many people are groaning right now. I wish my computer had some, come on, the little computer that could. Within 3 standard deviations, we expect to see 99.7% of the data. Okay, that means if we do some simple math, 99.7 minus 95, 9.7 minus 95 gives us 4.7%. So 4.7% is shared in between these 2 areas here. So that means if you divide by 2, 2.35% of the data is held within 3 standard deviations, and 2.35% of the data, 2.35% is held within the third and the second here, and within the second and the third here. And then lastly, 100% of the data must be held under the whole curve, right? The whole area has to add up to 1 or 100%. So if you do that last little bit of math, see if you can pause the video, tell me how much are going to be in the tails. You do 100 minus 99.7. So in this last little chunk down here, we have 0.15% past the third standard deviation and 0.15% past the third standard deviation there. So basically, the bulk of the data can be expected to be seen within 3 standard deviations. The large majority, leaving out very little, can expect it to be seen within 3 standard deviations of the mean, which is pretty cool. Now we can use that to do some calculations. Now, what you have to realize is some of these normal distributions take on different shapes. So if you have one that looks like this, and you're trying to figure out, like, let's say it gives you values, and you know the mean is right underneath this curve, that's fine, and you want to figure out what the standard deviation is. Let's say this is 50. One trick you can do is you can try and find that point in statistics, in calculus, it's called the inflection point, where it changes from, it's straight, so to speak. The other thing that you can do is you can go out to where the curve touches the horizontal axis or gets really close. That's going to be roughly your third standard deviation. So then you can just subtract these and say, well, that's 30, and then divide by 3. So that tells me that my standard deviation is roughly 10. So that would go to 60, and then 70, so on and so forth. So you go out to where it touches and then divide by 3 to figure out what your standard deviation is. So if I had to guess, I would say standard deviation is 10. Okay, great. So here it is in all its glory. This rule that I just showed you has a name, and I would like you to label it in your notes, and you need to be able to reference it on the AP exam and on this test. It's called the empirical rule, or if you don't want to remember the name, the empirical rule, you can say the 68, 95, 99.7 rule, whichever one you like best. Here are the more accurate percentages for the empirical rule or the 68, 95, 99.7 rule, and we're going to be continuing to use that. Take a minute to jot that down. I'm going to move on. So here we go. So why do we use normal distribution? So they were first kind of discovered by Gauss. Now, if you had me for Algebra 2, he's also the same person that discovered, or like kind of, he discovered the fundamental theorem of algebra, or formalized that. So that's pretty cool. He's just Euler or Gauss basically did everything in math. Pretty much if you go back far enough. So like the tests that you guys take in class should roughly follow a normal distribution. Gauss was looking at people taking measurements, should roughly follow a normal distribution. Characteristics of biological populations, so like if we were to take the weight of Labrador retrievers, that would probably follow a normal distribution. Flipping, counting chance outcomes and seeing the results will follow a normal distribution. And like a lot of things with law and crime, like skid marks on a road, when someone slams the brakes on, you can actually use that to kind of predict the distance, and those are going to have, at a certain speed, a normal distribution of skid lengths if you're going, say, 60 miles per hour. So you can use the skid length to deduce how fast the car was going, so on and so forth. And we'll see that example resurface. Okay, so really quickly, I'm going to jump out of here, and you do not need to know this for my test. You don't need to even know this for the AP exam, but I wanted to show you that the density curve for a normal distribution has an equation, and it's a monster. It's absolutely brutal, and I have taken the time prior to recording to plug this into Desmos, and I've put some sliders. A in this case is the standard deviation on my slider, and B is the mean. I just pulled that straight from the equation. Now when I change the mean of the distribution, it moves the bump left and right. Okay, so there we go. There's the normal distribution in Desmos and this horrifying equation. And when I change the mean and make it, when I change the standard deviation and make it larger, it spreads it out. When I change the standard deviation and make it smaller, it makes the peak extremely tall. Okay, very tall. So, turns out this one is called the standard normal distribution, where where's the 0.3999? Where it has area, they all have area of 1 underneath them. This one has a mean of 0, standard deviation of 1. We'll come back to that. So I told you I wanted to show this to you, so there's this horrible equation. So let's actually do some math with these now. Here's the distribution of 2020 SAT exam scores. Now you can see the density curve. Notice that it doesn't follow the top of it's not like the blanket. It's kind of following roughly where the center of the peaks are for the most part. So this is the density curve that was calculated for the 2020 SAT scores. So let's go ahead and take a second to estimate the mean and standard deviation of these SAT scores. So to find the mean, we simply look at the peak and trace our way down. It seems to be that the mean in this case is 1150 for SAT scores. So how do we find the standard deviation? Well, there's two ways. You can try and find that inflection point where it looks like, it's straightened out, where it goes from facing down to opening down to opening up, or you can go out to where it kind of touches the line and then divide by, subtract the mean from that to figure out the distance and divide by 3. So if you do 1600 minus the mean, which is 1150, you get 450 divided by 3, which is 150. So if you want to see that calculation there, I did standard deviation. Looks like it's about 1600 minus 1150 divided by 3, because 3 standard deviations to the right should hold most of the data. That's 450 divided by 3, which is 150. Now, one thing to keep in mind here is, Mr. Sligo, why aren't you using X bar and S, the sample standard deviation? Because if this is, we have the data for every single SAT score from 2020. So this is the entire population of SAT scores, which is kind of cool. So you can see this contained all the way over this direction. All right, cool. So we know what the mean and we know what the standard deviation is. Now we can do some calculations about what percent of SAT scores were less than 850. So here's my mean, here's mu. Where's 850? 850 is down here. So now I have to sit and say, all right, how many standard deviations from the mean is 850? Well, I know that one standard deviation is 150, so I go one standard deviation down, then a second standard deviation down. What percent, approximately, what percent of 2020 SAT scores were less than 850? All we have to do is get the area under the curve, but that should be easy enough, because this is minus 1 standard deviation, minus 2 standard deviation. So I go back to my chart. To figure out what that is, I'm going to go back to my empirical rule, which is right here. All I have to do is, to the left of 2 standard deviations is 2.35% plus 0.15%. So 2.35 plus 0.15 is roughly 2.5%. So using that empirical rule, let's do that really fast. So to get that area, all we have to do is those 2 little blocks that we added up, which is 0.15% plus 2.35%, which is equal to 2.5%. So 2.5% of the SAT scores were less than 850, about 2.5%. Okay, what about the next one? What percent of 2020 SAT scores were greater than 1,000? Okay, well, 1,000 is right here, and 1,000 is minus 1 standard deviation away from the mean, which is 1150. Except this time it says what percents were greater, so we're actually looking for the area under this curve over here. And so to do this calculation, all of this area in this chunk, there's a couple ways we can do it, but probably the easiest way is to add up all the chunks to the right, which will be 68% within 1 standard deviation, or 34 plus 34. So it'll be 34 plus 34 plus within, so we have this chunk, and then there's the second, or so there's the first standard deviation, there's the second standard deviation, there's the third, and anything after that. So it would be 34 plus 34 plus 13.5 plus 2.35. Well, we could really just say 2.5 there because we know how much that is, but that's okay, plus 0.15. So we get a total, what percent of SAT scores were greater than 1,000? 68 plus 13.5 plus 2.35 plus 0.15. Sorry, the president was calling me, aka my wife, I think. So that is 84%. So 84% of the SAT scores in 2020 were greater than 1,000. Okay, a couple more. And then you could do like areas in between as well. So how many were between 1,000 and 1,300? Well, that's within 1 standard deviation, and I know that those are the boundaries for my standard deviation. So that one is going to be a quick 68%. Hello, dear. I'm recording a video. Can I call you back? Okay. All right. Love you too. Bye. Persistent. She's persistent. 68%. Okay, great. That's why I married her. Okay. Warning, though. I have to say something really quick, and that is you can't do this, the thing that I'm currently doing, on a distribution that's non-normal. This only works for normal distributions. So what do we do for all the other distributions that are shaped? Is there a rule that covers every statistical distribution? And it turns out that there is. This guy's name, I'm going to butcher it. It's Pafnuty Chebyshev. So this is Chebyshev's rule. And it states that at least 100 times 1 minus 1 over k squared percent of all observations are within k standard deviations, I spelled that wrong, of the mean. So if you want to know for any distribution or every distribution, how much of the data should fall within, say, k equals 2 standard deviations, well, all you have to say is, well, I can tell you how much. We do 100 times 1 minus 1 over 2 squared percent, which is, well, 1 over 2 squared is 1 over 4. 1 minus 1 over 4 is 3/4. So this is 100 times 0.75%, which is 75%. So according to Pafnuty Chebyshev's rule, it doesn't matter what the distribution is, at least 75% of the observations are going to be within 2 standard deviations. So he was extremely conservative with his guess, but it covers essentially every distribution type and shape. Fantastic. Thank you. And here are some other distributions that you can look at. That's basically it. Your assignment's posted on the class website. Thanks for watching the video. I will also upload this. This will be on YouTube to watch over and over again if you need to. Yeah, I'm going to call back my wife. We did it. See you later.